Morning, just a brief video on density altitude. We've covered this already in Fundamentals of Aviation, and you can read all about it in the Pilot Handbook of Aeronautical Knowledge, reading assignment of Chapter 11. Density altitude is an important first element as we get into performance charts, and we're going to go deeply into that here in just a little bit. You need to know about density altitude, of course, but also its relationship to the performance charts, all of which will be on the written private pilot written test. This graphic is sort of a cool little demonstration of things that you need to check, not only for takeoff performance, but also for cruise performance all the way around. Whenever you fly, we fly in an atmosphere, right? And altitude, temperature, humidity, all of those are factors in the performance of our aircraft. All of these factors influence airfoils, whether it's the propeller efficiency or the wing efficiency. From earlier studies, we talked about the atmosphere and atmospheric pressure. We talked about the fact that air does have weight. Our atmosphere has weight, so there'd be higher atmospheric pressure at lower altitudes and lower atmospheric pressure at high altitudes. That's directly related to the performance of the airfoil. The airfoil being either the wing as an airfoil or the propeller as an airfoil. So as we climb at higher altitudes, there is lower air pressure, less performance. That's why most aircraft have a ceiling, which is not certified to fly any higher than that particular altitude. And this, of course, is the major factor related to performance numbers. For example, here's a demonstration of takeoff at a high density altitude at a higher altitude. We have the first diagram here is a takeoff roll of 1,300 feet at sea level, density altitude at sea level, and you're going to climb at 1,300 feet a minute. But if we climb up to density altitude of 5,000 feet, and that may be an airport at 5,000 feet above sea level, or it may be density altitude at 5,000 feet, it's going to take a longer distance to get off the ground, and you're going to climb at a lower rate of climb. That's why it's important, because you may have obstacles at the end of the runway. You may have a runway length. You're taking off on a short runway, so that's why we need to be aware of density altitude, its effect on performance, because the next step is to talk about charts, performance charts. Here's an example, and this is not an accident I've seen, but there's a picture of a fellow presumably took off without checking all these numbers on a hot day, perhaps a hot and humid day, maybe even a high altitude airport, and he simply had not enough performance to get off the ground and ended up in the bushes at the end of the runway. Happily, it doesn't look like a fatal accident, but there are fatal accidents involved with the fact that people aren't taking into account the density altitude. I'm not trying to scare anyone, just saying that this is an important issue. Here's the principle here, high density altitude. What that means is if the pressure is going down, lower pressure as we climb to higher altitudes, or as the temperature goes up. As the temperature goes up, we've talked about it before, the molecules move further apart. Hot air is less dense. That's why a hot air balloon will climb. And of course, we've talked about that in the weather section. These heated bubbles of air rise into the atmosphere and cause perhaps turbulence, and eventually, if it's unstable air mass, could be severe weather as well. So if it gets warmer, if the pressure goes down or the temperature goes up, we call it high density altitude, which means performance is less. However, if the temperature goes down or the pressure goes down, that causes thicker air. We also know that there's two standards. We have 15 degrees. C is the standard temperature. This is where all of the performance figures in your books, in your aircraft manuals, are going to be based on 15 degrees C as being standard, and pressure altitude will be based on 29.92 inches of mercury. Right? That's the standard. This has to be memorized. That's what performance figures are based on to start. Humidity also has a small factor, so this is just you need to know, but we have no way normally of telling what the humidity is on a particular day, so we don't take, it's a small factor, so we don't normally take that into effect when we do go through the performance charts. But the principle is the same. The more humid the air, the more moisture is in the air, and the molecules are further apart. The air, hence, is thinner. No need to dwell on that, but that's just a fact that you need to know. It's just not included in the performance charts because it's a smaller factor. Temperature and pressure, altitude are the big ones. So we come to this chart. There's two ways to find out. Three ways, actually. There's density altitude chart like this. There's an actual formula that you can work through. And then there's some of the aircraft performance charts will include that as part of the calculation. But you will need to do this for the written test. But you know how to do it. It's not that complicated. We have covered this before. But first off, we take the local altimeter setting because we need to find pressure altitude. How do we come up with pressure altitude? Well, because at each station we'll have perhaps different altimeter settings. So we find the altimeter setting. For example, if it says 3100, altimeter setting 3000. I'm sorry. Erase that. Hang on. 3100. That means the air is thicker. More pressure, right? So the air is thicker. So we take the conversion factor of where's our airport? Or let's just say we're at 1,000 feet. MSL, that's the airport elevation. So we subtract 963 from that, and that gives us the density altitude for that particular situation. So let's see, that'd be 7, this is 3, this is 37 feet. Oh, 37 feet. So that's the pressure altitude. Okay. So the airplane thinks it's at 37 feet, even though you're at an airport at 1,000 feet. Capiche? Okay, so we take that pressure altitude and we go over here because we have another problem. We have to, that accounts for the pressure change. Now we have to account for the temperature change. So down here is the scale for temperature. It's in C and it's in F. So we have, typically in a weather report, you're going to get centigrade, or Celsius rather, I'm sorry. So let's just say it's 32 degrees, a hot day. So here's 32 degrees. So that will be where we go up on this line here until we meet 37 feet. Well, there's sea level. So sea level, this is the pressure altitude line. See, pressure altitude, sea level. So 63 feet is pretty close to sea level, right? So we're just looking for just the hair above that. So we follow that line up to there. All right. Follow me. So now we've corrected for temperature, corrected for sea level. Then we zip on over here with a straight line, hopefully. And it says airplane thinks it's at 2,000 feet. You can see the big difference temperature makes. It's at 2,000 feet because of the temperature only. So you went down to 37 feet, but now the airplane, because of the temperature, thinks it's at 2,000 feet. Thinner air, less performance. Okay. All right, I got to do another example, but I have to erase all this. Stand by. We'll do another example. The other way around. Let's see. Okay. Let's say, though, that the altimeter setting is 2930. So now we look over here, 2930, 294, 2930 is here. They're just leaving the zeros off, typical in aviation. So the conversion factor, the airport elevation, we'll say it's still at 1,000 feet, MSL. That's the airport elevation. So now it's saying you have to add 579 feet to that. Poor planning on my part. Okay, so let's see, 975, so 1,579 feet pressure altitude. So that's our pressure altitude. So now we got to find out we'll go check the weather report, find out what the temperature is, and say, oh, let's just say it's still 32 degrees. Very hot day, of course. 32 degrees is 90 degrees, but that happens. And this is a typical scenario where people get in trouble when it's a very warm day. So the pressure altitude is 1,579 feet. The airplane thinks it's that. You're at an airport at 1,000 feet, but it thinks it's 1,579 feet. But you got to correct for the temperature. So same thing, we got 32 degrees right here. So we go on up until it gets to 1,579 feet. So there's sea level, there's 1,000 feet. This is pressure altitude again. 1,000 feet, 2,000 feet. So halfway between 1,000 and 2,000 is pretty much that line right there. I have to make up my own line. So you go up, hit that, and go straight over, and try to make it straight. If you have a piece, you'll have a piece of paper. Just make a straight edge over there. But anyway, 30, I don't know, maybe 3,300 feet, 3,200 feet. Density. $3,200 feet. Big difference. 1,500 feet, it's almost, well, pretty much double. That's pretty high. You're going to have a hard time. You need that number there, 3,200 feet, in order to go through the performance charts in many aircraft, but not all. We'll go to the next slide, and here's an example of a chart. This is a chart that comes on the FAA test, by the way, that includes that calculation. So you don't have to use that other chart. You go to this chart, you start over here, and you have outside the question, of course, or your problem on that particular day of flight will include what's the temperature. Their example here, they usually give you an example so you can follow it. They're saying it's 13 degrees, 60 degrees outside Fahrenheit, or 13 degrees C. So you go on up. You still the same kind of calculation, same kind of chart. You go up till you get to the pressure altitude. So you got to figure out the pressure altitude. So there's still some calculations to be done. You have to come up with pressure altitude, which is simply that correction on the previous chart. And you find the pressure altitude. Their example here is that 4,000 foot line, and they grade over here to what's the weight of your aircraft. You come down till it hits the weight of the aircraft, which is 2,400 pounds in this example. Then you come out over here and you take the wind. What kind of headwind do you have? They're saying 8 knots, so you go down to 8. Okay, then you go straight over here, and it tells you guidelines not applicable for intermediate obstacle heights, right? So they're just saying that, oops, you're supposed to go up here, that's going to take you 1,400 feet to clear an obstacle at that distance. The point of the thing is, at this point, for you all, just understand that some charts are going to include that calculation, so you can miss a step. You still, in this case, you also need to know pressure altitude. You have to calculate that. But it gives you the temperature conversion, if that makes sense. And here's another chart that you'll need to have density altitude calculations, but they're helping you as much as they can. They're saying, what's your pressure altitude? You got to figure that out. You got to come with pressure altitude. You have to make that calculation, not just read what the altimeter says. You have to make the correction. It is telling you the ground roll at 0 degrees. So if it's 0, but of course standard is halfway between these two, 10 and 15. They're saying, so you have to sort of figure that out. You have to figure out the pressure altitude, but it's giving you the correction for temperatures. On a standard day, it'd be halfway between this. So if your pressure altitude is 3,000 feet and the temperature is at 0, it's going to take 970 feet before your wheels leave the ground, basically. And if you want to clear a 50-foot obstacle, it's going to take you a little more. But if it's 15 degrees, we've got to extrapolate between this number and this number, halfway between those two. Because there's a 10 degree and there's a 20 degree, there's not a 15 degree. So if it's a standard day, you've got to extrapolate between the two. You can add them up and divide by 2 if you wish. That's the easiest way to do it. Again, you start with pressure altitude in these particular cases. So just so you know, and we're going to be getting into charts soon, so understand what the effect of density altitude is. That way you can logically look at a number and say, well, wait a minute. My calculations say it's on a hot day, it's going to take a shorter distance to take off. That doesn't make sense. So logic has something to do with our calculations. Also, something you may not have considered, we haven't considered it in class, is that there are calculations for how long it's going to take us to climb. We were planning some flights at 3,000 feet, and we were saying, well, the ground speed is going to be this, and how much fuel we're going to burn. We didn't take into account the fact that you're not leaving, you don't take off at 3,000 feet. You have to expend energy and fuel to climb to 3,000 feet to begin the flight. And that is going to burn more fuel. So they're telling you, again, you need to find out what the pressure altitude is, but then they're giving you these corrections for temperature. So this is, they're telling you what is standard at that temperature. At 1,000 feet, standard temperature is 13. At 2,000 feet, standard temperature is 11. So they're calculating that out for you. So if you're flying along, or if you know what the temperature is at 3,000 feet, you have to climb to 3,000 feet. If it's higher than standard or lower than standard, you would be able to extrapolate some stuff here. At any rate, it's pretty simple. Again, I want you to read chapter, where is it here? Chapter Performance, chapter 11 of the Pilot Handbook of Aeronautical Knowledge, and it will help you with this. I've exceeded the length of this video, honestly. We'll work through this stuff in class, but this is just a basic introduction to pressure altitude as it relates to performance charts that we'll be getting into. Thank you.